Hello class, welcome to this lecture on design of brakes, which is part 3 and this is last in the series on design of brakes. In this lecture we will look at some of the problems on block brake design and band brake design. Now the first problem is on block brake. It reads like this: the block brake as shown in figure provides a braking torque of 360 Newton meter. The diameter of the brake drum is 300 mm. The coefficient of friction is 0.3. So given these things, we will need to find out the force P to be applied at the end of the lever for the clockwise and counterclockwise rotation of the brake drum, and the location of the pivot or fulcrum to make the brake self-locking for the clockwise rotation of the brake drum. Now this is the configuration of the diagram of the block brake as per the given dimensions. The drum is rotating in the clockwise direction. This is the block, the tangential force, which is acting at a distance of 50 mm from the fulcrum point, and the fulcrum point distance from the center of the drum is 100 mm, and the total length from the fulcrum point to the point of application of P is 800 mm. Now for the case 1, wherein we need to find out the force P for the clockwise rotation of the brake drum and also for the counterclockwise rotation of the brake drum. Now for this configuration, we know that, or in general, the braking torque is the tangential load times the radius of the brake drum. TB is given 360 into 10 to the power of 3 Newton millimeter, Ft into 150 millimeter. This is the radius of the drum, 150. So hence the tangential force Ft is 2400 Newton, and by using this relation, the normal force Rm is 8000 Newton. Now for this case, the braking torque is given by this equation: Tb equal to mu P L into R divided by x plus mu N. Now for the first case, wherein the drum is rotating in the clockwise direction, what should be this force magnitude? We know this equation, and by rearranging this equation, we get the P equal to Tb into x minus mu A divided by mu into L into R. So all these things are known. Hence we get magnitude of the force P as 1850 Newton. Also, by using the first principles, if you want to solve or calculate the magnitude of the force P for this configuration and for the equilibrium of all the forces, you can take the moment of all the forces about point O and get this equilibrium equation, and from that equilibrium equation also you can get the magnitude of this force P, which is found to be 1850 Newton, as same as that of this obtained from this equation. Now similarly, for the counterclockwise rotation of the drum, the force P is again, either you can use this equation, or again you take the moment of all the forces upon this point, right? But only thing is Ft is in this direction in this case. So hence for this case, the magnitude of the force P is 2150 Newton. So compared to the previous one, where you have 1850 Newton when the drum is rotating in the clockwise direction, now it is 2150 when it is rotating in the counterclockwise direction. Just note that. Now second part of the problem is to find the location of the pivot or fulcrum, this point, to make the brake self-locking. Now the clockwise rotation of the brake drum is shown in this particular figure. Now let x be the distance of the pivot or the fulcrum from the line of action of the tangential force. Okay. Now from this line of action, of the tangential force to the fulcrum point O. What should be this distance in order to make the brake self-locking? Right? Now we need to find out this distance between the fulcrum point O and this line of action of Ft, so that the magnitude of this P is 0. That means the brake becomes self-locking, wherein you don't have to use extra mu of P in this case. Now let us start. For this configuration, let us take the moments about the fulcrum point O, P into 600 plus 200 about this point, then Ft into x, Ft into this. Now it is x not 50, right? So in order to make the brake self-locking, what should be this distance? That we are determining. So don't use 50. We have taken this as now x millimeter. So Ft into x minus Rn into 200, Rn into 200 anti-clockwise moment. So must be equal to 0. So hence, in order to make the brake self-locking, this quantity Ft into x must be equal to Rn into 200. Hence P will be equal to 0 automatically. Therefore, Ft into x equal to Rn into 200. So if we equate these two, because Ft magnitude we know, Rn magnitude is also known, and so only unknown is x. So hence x will be equal to 667 millimeter. So from this to this, what should be the length? 667 millimeter in order to make the brake self-locking. Or otherwise also you can use this equation and find out the value of x. Now problem number 2. It is also on shoe brake. Figure shows a brake shoe applied to a drum by a lever AB, which is pivoted at a fixed point A and rigidly fixed to the shoe. The radius of the drum is 160 mm. The coefficient of friction of the brake lining is 0.3. If the drum rotates clockwise, find the braking torque Tb due to the horizontal force of 600 Newton applied at the horizontal force of 600 Newton applied at K, that is end of the lever. Now let us find. Now this is the given block brake configuration arrangement. The lever is like this, and this P is in the horizontal direction. Now let Rn be the normal force here, Ft be the tangential force, which is equal to P into Rn. Now as usual, taking moments about point A, about this point of all the forces, we get Ft equal to 372.8 Newton. And also we know that braking torque Tb is Ft into R, the radius. So here it is substituted in terms of meters. So hence braking torque is 59.65 Newton meter. Problem number 3 is a problem on band brake. A simple band brake operates on a drum of 600 mm in a diameter that is running at 200 rpm. The coefficient of friction is 0.25. The brake band has a contact angle of 270 degrees. One end is fastened to a point, a fixed pin, and the other end to the brake arm 125 mm from the fixed pin. The straight brake arm is 750 mm long and placed perpendicular to the diameter that bisects the angle of contact. See, this is important, bisects the angle of contact. So the lever or the brake arm is so placed that it bisects the angle of contact. In that case, what is the pull necessary on the end of the brake arm to stop the wheel if 35 kilowatt is being absorbed? What is the direction of this minimum pull? Then second is, what width of steel band of 2.5 mm thick is required for this brake if the maximum tensile stress is not to exceed 50 megapascal. Now read the problem carefully, and after reading you have to draw this sketch. Now you see this arm it is actually bisecting. This pivot point is so located that this is bisecting, okay, the angle of contact. So it got 270 degrees, so equal on this side and equal on this side. Now the simple band break is shown here. Since one end of the band is attached to the fixed pin O, this is attached to this. Therefore, the pull P on the end of the brake arm will act upward, and when the wheel rotates anti-clockwise, the end of the band attached to O will be tight. So this will be tight side, and its tension is T1, and the end of the band attached to point B, here point B, will be slack side with the tension T2. So now this is the arm or lever OBC. Okay, OBC is the lever, and the tension T1 is the on the tight side and T2 is on the slack side, and this is the angle of contact, right? The angle between points L and M. We know that the ratio of tensions is given by 2.3 log T1 by T2 equal to mu theta. We know theta here to be substituted in terms of radians. 270 degrees, 4.713 radians. Okay, hence we get T1 by T2 equal to 3.25, and let this be equation number 1. And let T be the braking power. We know the power equation, P equal to 2 pi nt by 60 into 1000. So this is the power. N is speed given 200. So hence TB braking torque is 1667 into 10 to the power 3 Newton millimeter. Also we know that braking torque is given by T1 minus T2 into R. So TB equal to T1 minus T2 into R. So R is 300 millimeter. So hence the difference T1 minus T2 is 55-57 Newton, and let this be equation number 2. By using this equation and this equation, we get the tensions on the tight side as 8027 Newton and tension on the slack side as 2470 Newton. Now for this configuration, taking the moment of all the forces about O, we have P into 750 equal to T into OD, which is equal to T2 into this. How OD is obtained, it is mentioned here. Okay. Now width of the steel band. Okay, we know that the tension on tight side T1 equal to sigma T into W into T. W is the width of the belt and T is the thickness of the belt. This is given, this is given, T is given, W is unknown. So hence the width of the band, steel band used in this band brake is 64.2 millimeter. Thank you students for your attention. See you in next class.